Gotcha.
I think we can get started. So, since this is Nish's first time attending and speaking at the seminar, maybe I'll just briefly introduce him. So, Nisch did a math undergrad at NYU and then went to spend some quality time doing cybernetics or something like that with Catherine Danielle at ANU, who is an old friend of mine, and many current and former students of hers sort of turn up on the Discord from time to time. So that's quite interesting to me. And now he's doing a work in theoretical neuroscience in Israel and working on grid cells and stuff like that, which has also come up in the neuroscience seminar here, and maybe we'll hear about at some point in the future. But today he's going to take us through the Saxe-McCelland-Ganguli paper on semantic development in neural networks, which is closely related to some of the topics in deep linear networks that were discussed a couple of months ago, and many of the other things that we're interested in. So thank you very much, Nisch, for preparing the talk, and you can begin when you're ready.
Yeah, thank you for the introduction. I'm very excited to be here and take this as an opportunity to start learning more about SLT and stuff also. And although I can't see who's here, nice to meet you all. And I'm going to present this Saxe-McCelland-Ganguli paper on learning dynamics of linear networks. So that's the focus. So the idea being that while the linear networks themselves are, of course, linear machines, the stochastic gradient descent dynamics on the network are going to be nonlinear, and we can try to gain some insight, maybe even generalizable insight, by looking at this learning dynamics in these networks. And in the paper, they start by making this distinction between a shallow network versus a deep network. So a shallow network is basically something of the form just y hat ws as for shallow x, and where w is the learnable parameter. So there's some data points x and y, and we're going to make predictions, but just by doing one matrix multiplication with x. For deep networks, it's basically the same format, but it will be written as some product of d layer weights. In particular, we're gonna focus more on like W1, W2. I'm just trying to get the numbering right. This network, and see the distinction between these two, how they differ, difference in learning dynamics. Of course, what they end up learning is basically the same because they are both linear. Right. This is why I wanted to check that. It's W2, W1. Yeah. And the data set is basically you have xi, yi, and I goes from 1 to p. And on top of that, there is, of course, the loss function, which in this case, for set w, is just the mean square, or in this case, we're going to look at error per example, because this is going to be stochastic gradient descent with batch size 1. That's the setup here. The loss is going to be calculated for each element at a time. Great. It's not going to be so useful for us to keep track of the dimensionality, but basically the input x is of dimension n1. There's a hidden layer dimension n2, h, and then there's the output layer, which is n3. So this is kind of broad setup, and we're going to focus on how the SGD learning dynamics works in these two different cases, shallow network and deep networks. And I'm going to do a sort of inversion from the paper, I'm going to start with the shallow network just to show like crucial assumptions and kind of moves that they make throughout, so that we can easily replicate that in a slightly more complicated case of deep network. So I'm going to try to move the board.
Yep, so if you just move yourself over this way. Yep. Great.
Okay, cool. Great. So we start with the shallow case. And please feel free to ask questions and confusion, and if I make any mistakes, feel free to correct me. So this is the loss function, and we are going to do a stochastic gradient descent on top of this loss function. So the learning term, the correction term coming from the gradient descent, can be written as...
I think you're missing a sum over I.
Basically, no, so here we start with calculating this only over one sample at a time, and then we will do the sum at the end.
Oh, so you're ill.
So this
maybe
is
you
like,
should have an I in it then. Yeah, okay, I get you.
Yeah, that's right.
Mm-hmm.
Yeah. Batch size 1. Right, so with some, and then now we introduce some learning coefficient minus lambda, and we take the derivative with respect to the W here. This is a standard matrix derivative, which is my 1 over 2 times 2 yi minus wx times xi transpose. So if you want to convince yourself of that this is a correct derivative, you can sort of check the dimensionalities of the matrices and vectors here to see that it works out, but this is the derivative in the simple case. Great. So now we're doing all of this derivative with respect to one element at a time. So what I've written here is not quite correct. This should be a function of I. So it should be something like WSI, because we're doing one element at a time and then updating for the next element and so on. So the weight here itself is a function of I. And now I'm gonna start showing some of the assumptions and kind of approximations they do. So the first one is they define time in this way, where t equals to 1 when all 1 through p samples have been presented. And time equals to 2 when they have been presented twice, so 2p samples have been presented, and they don't necessarily need to be in the order, in any order, but all of them need to be presented once. So that's what defines time here. And then they make this assumption, which is pretty important and maybe interesting here, because this assumption is the assumption of very slow change in weights, which maybe if something like phase shift is happening or something would not be true. I don't really know, but they make this assumption anyways, which is that throughout each time where they present 1 through p example, time equals to 1, all of these WSI are going to be the same value W2. So they don't change. Each presentation of example it does not change the WS themselves so much. So it's only the change accumulated throughout the training time that sort of matters here.
Mm-hmm.
Okay, now trying to move. Great. So now we can write this loss over for each time window. We can now start defining the loss by summing over all the examples. We sum over the p examples, and we get lambda yi minus wst xi transpose. And this sum, of course, can be now written as like the expected value. So when we move this inside, something like lambda sum yi xi transpose minus wst sum xi xi transpose, and we're gonna replace this is sum over I. We're gonna replace this with expectation y x transpose, and this with expectation x x transpose. And in particular, this term is going to be pretty important here, and it's going to be this is the kind of cross covariance term, and it's going to be denoted with these symbols. Mm-hmm. So there's sum over p-value. We're replacing each instance with the mean. So we have lambda p times and so on the left hand side, then they take the continuum limit. I don't really know how to even define this limit properly and like show that it's correct and so on, but assuming it's all fine, they just write it as dws over dt. And moving this quantity on the left here, it gives us the time scale, which is tau is going to be 1 over lambda p. So all of this together, we get tau dws over dt sum yx minus ws sum x. So this is the equation now we're going to be analyzing. Great. And the crucial step that they make now to analyze here is change of basis. This is important. Change of basis. And they emphasize this change of basis is done after calculating the gradient, not before. And this is important because if you did the change of basis before calculating the gradient, your learning dynamics would look different. You would be doing calculating your derivatives over different variables and so on. So now it's important to emphasize that change of variable is done after the fact, and it represents the same old gradient descent with respect to the W's that we started with. So how do we do this change of basis? We do this by singular value decomposition of the cross covariance term. So this SVD exists and then can be written as something like U as V transpose, where you sum over the rank of this covariance, cross covariance matrix, and you get S alpha U alpha V alpha transpose. And these U and V are going to be the kind of left and right eigenvectors, and we're going to project everything in the dynamics to using these left and right eigenvectors, and going to try to simplify the equation so we can kind of solve it analytically. So given the introduction of U and V, now we're going to define WS in the following way. Define W hat S such that WS is U W hat S V transpose. So W bar would be kind of the when you project W in this space of left and right eigenvectors coming from the cross covariance matrix. And further, we can note that for this kind of SVD decomposition, U transpose is equal to V transpose is an identity matrix. So now we substitute and we write GGT is U W bar S V transpose. This is just from the equation before, equal to YX minus U W hat S V transpose. And now you multiply on the left with U, on the right with V, and things simplify, and you end up getting tau d dt is just going to be here. When you multiply on the left and right, given that we know this will just end up being the diagonal matrix S, and on the right you'll just end up getting W hat S. So this is a slightly more simplified form, but now here we need to make some more additional assumptions to take this forward. Where am I going?
We can get rid of these figures and I'll put them up a bit later since you're in the middle of the calculation. How's that?
Yeah, that sounds good.
Okay. So you can return over here and write on these boards.
Gotcha. Okay. Thank you. I was not trying to run off in the middle of
you might want to walk away from the boards just a little bit so that your head isn't filling up the screen.
Oh, okay.
That's good.
Is that better?
Yep.
Okay, cool. So now there's another assumption here, which is that this quantity W bar S is at time 0 is diagonal. We are making this assumptions because the only other variable that shows up is this S, which is a diagonal matrix, and if we make this assumption, everything kind of nicely decomposes, and we can work with this easily. They also say in the text that this is not so crucial, that as long as you kind of initialize W randomly, all the values of the diagonal of W hat S will kind of decay very quickly, and all the evolution will lie in W hat S diagonal values. I kind of can see it, but I'm not sure why exactly that needs to be true, but this is what they say. And in particular, we can now define all the matrix only by defining the diagonal terms alpha alpha as B alpha. And once we do that, the whole sort of differential equation that we have decomposes into a bunch of 1D linear differential equations, tau d B alpha over dt is equal to S alpha minus B alpha. And immediately we can see that when this is 0 at fixed point, S alpha equals to B alpha. So the dynamics is gonna take the diagonal element of W bar S such that it at infinite time converges to S alpha. And in fact, this is a 1D linear differential equation, so we can try to, we can explicitly write down the solution here. And that would be B alpha t is S alpha 1 minus e to the power t over tau plus B0 alpha e to the power t over tau. I'm not going to go through the steps of doing this, but we can do this. And if we have time later on, we can maybe talk about timescales too, in which case this other equivalent form of writing this might be useful, which is something like we can write this in terms of time itself. So t can be written as like tau ln S alpha minus B alpha at time 0 divided by S alpha minus B alpha at time t. So this might come useful later on when we're going to talk about timescales, but right now I'm just writing it. Great. So what did we end up seeing here is that these quantities B alphas are going to evolve such that they just saturate to S alphas. As time progresses. And this will kind of be the learning dynamics for the shallow case. And it sort of makes sense. We're just like learning all the modes and the eigenvalues, singular values corresponding to them and getting to them very quickly. But what's going to be different is that this dynamics will look different, will be different for deeper networks. And that's where all the kind of interesting things come in. So here I have done kind of the introduced the notion of time in this context, like showing all the example, all the assumptions they have, and so on. So now we can go on and kind of do the same calculation for the deeper network case, which is the one that we're actually interested in. Okay. So this one I'm going to do maybe slightly quicker, both because not that much time and because we've seen kind of the main crucial moves that needs to be made here. So
maybe we can move to a new set of boards if you're going to use up more than one, I think, right?
Yeah. Where should we move? Yeah.
Yep. Follow me. Yeah, you want to take that with you. Just a sec. Yeah, so you want to reattach a speaker, and then just run.
Great.
Awesome.
Cool. So yeah, I'm sorry, my handwriting is big, so it's taking up a lot of space. But so now we move on to the deep network case. And all of this kind of generalizes to much deeper networks and so on. But just for the presentation, I'm going to focus on a two-layer network, W2, W1X, and loss as before defined as 1/2 yi minus y hat I square. Cool. Here we do the derivatives, and we write the correction term for each one of them. Again, this is a fairly straightforward matrix derivative, so I will not write all the kind of details, but what you end up getting is lambda W2 transpose yi minus y hat I xi transpose. And here they define this HIT, which is like hidden variable, and hidden variable is just W1X, just this part is H. Cool. And as before, both for W1 and W2, this I is going to stay, the weights are going to stay constant throughout the training period within a given epoch, and the epoch corresponds to time t. Cool. And then we can do this calculation here by summing up all the learning we have done within the epoch. So we get lambda W2. This is just already T transpose yi minus, I'm going to write this y hat more completely, W2T, W1T, xi. Times xi transpose. Great. And as before, we can now start doing the replacing the quantities by average. So we got this lambda p term outside. There's this W2T term here, and you get the cross correlation from here and here, these two interaction. So we get yx. Sorry, this bracket is in the wrong place. And here you get W2T, W1T, sum x. So this is the update that happens in one epoch for weight 1. And similarly for weight 2, I'm just going to write this directly because it's basically doing the same thing. Wherever there's like interaction between y and x, you replace by cross covariance matrix. Wherever there's interaction with x and itself, we replace it with the sigma x. Great. And as before, if we do the limit, we can replace the left-hand side with like dw1 or 2 dt with time scale corresponding to 1 over lambda p. And then comes the crucial change of variable. So we have this cross correlation matrix again written as U S V transpose. There is an extra kind of degree of freedom here coming from the fact that there's W1 W2 interaction, and we can just insert a matrix between W1 and W2s and keep the things as they are. So we can do the following sort of change of variables. W1 will be R W1 V transpose, and W2 is U W bar 2 R transpose. And because what we're interested is W to W1, as long as this R transpose R is like an identity, then it doesn't really matter. So we have this degeneracy in the weight space already coming here, which again might be interesting for you guys because degeneracy, but maybe not.
Yeah, it definitely is.
Yeah, so and here they also make this, oh shit, did I mention this assumption before, where I just removed the sigma x term because this is identified as I, the identity matrix, and this is basically something like whitening the data. There is no cross correlation between the inputs themselves. They have this kind of example of where it might happen in brain. It's a sort of an interesting example where there's this area called, just for a little digression, called hippocampus, where the architecture of hippocampus looks something like you get a value here, and it gets massively projected to a much larger space, and then goes back down. And this is sort of where like semantic learning might be happening. And what they're saying is the X is coming from here. And because it's projected this way into something very high dimensional, X transpose is probably just going to be the I matrix, identity matrix, because everything's like projected to an extremely high dimension space. So this is their sort of justification of why doing this is probably fine. Cool. So as before, you can substitute the variables like these variables here into the equation that we just wrote and so on. I will skip the algebra. It's like 2 lines of substitutions, and you just write everything in terms of W bars. So I will just write what it will be. Tau W bar 1 over dt is going to be W2 transpose S minus W2 bar. Sorry, these are all bars here. W2 and W1 bar. Cool. And now, then again, they need to make this assumption here, as before, that W had both 1 and 2 at time 0 are diagonals. And in fact, they make this further assumption if the diagonal of W1 alpha alpha is C alpha and W bar 2 alpha alpha is D alpha, we are further going to assume they are like roughly equal. Again, in the text, they say that as long as they're sort of the same scale, same order of magnitude, things are fine. But for analytics, they're going to assume this. And then they're going to further define the term A alpha, which is a product of C alpha D alpha. Great. So what happens is now, like before, the equation that we just saw decomposes into linear one-dimensional differential equations on the variables on the diagonal. So we can start writing this as this set of two equations, which is tau d dt C alpha is G alpha S alpha minus C alpha G alpha, and tau d dt d alpha equals to C alpha S alpha minus C alpha. So here already you can start seeing that this term is defined as A alpha, right? And if this is the particular variable of interest that we're going to analyze, we see that its fixed point is going to be S alpha here already, apart from the other degenerate fixed point. But like this is the more interesting fixed point. So now we can, instead of writing the differential equation in terms of C and D alpha, we're going to write it in terms of A alpha. And you can kind of think of it as like what would happen if W1 and W2 were multiplied. They are just diagonal matrix, so all the diagonal variables would multiply with each other, and this would be like the actual kind of variable of interest for us. So we can just by the chain rule, we can write this as C alpha tau d dt d alpha plus G alpha tau d dt C alpha. Then you substitute these into the equation, and you end up getting something like 2A alpha S alpha minus A alpha. So there was something interesting of note already here, which is this equation has two fixed points, right? Like d dt A alpha can be 0 if A alpha is 0 or this quantity is 0. And I suppose one way of thinking why, we'll see later, one way of thinking why learning happens in this kind of nonlinear manner is the toggle between these two different fixed points. Like there's like pull from both of them. But we can look at that in more detail later on. Cool. So now, as before, we can solve this. This is a solvable differential equation. You can do some partial fraction decomposition. I did it. It's a little annoying, but I'm not gonna go through it here. So I will just write the solutions. Again, I'll write it in two forms so that it'll be interesting to analyze. One is what happens to A alpha t itself, and E2s alpha t over tau And also equivalently, you can write this in terms of like time. I'm skipping the index here because it's general. Cool. And how do they look like? I think in the first figure that Daniel, maybe you can put it up. They plot these variables, but these A alphas basically evolve like this. They are flat, and then they suddenly go boom. And there is this two thing to note. This higher values are basically as alpha ordered by their magnitude, and the time scale is also set by the order of like the value of S alpha. So the size of the singular value that they learn sets both the final value of A alpha, as we saw before, that is the fixed point, and also the kind of temporal time scale at which it reaches that value.
This figure or the other one?
Yeah, this one. So here, for example, in C and D, you can see the distinction between just the thing that we calculated. On D, there's the evolution of singular values through the shallow case, and on C, you can see these singular values evolving in this nonlinear case. And these they have this very clear separation of time scale where like strongest modes are learned first, and then the second strongest mode, and third, and so on. And this nonlinear learning behavior is quite interesting. And in fact, now we haven't quite shown that yet, but the actual weights that we're interested in can be returned in terms of this variable A alpha, right? So we started by saying W2t times W1t is basically U W bar 2t. There's this R transpose R term here, which is I, W bar 1t, V transpose. And we basically, by definition, these quantities are A t, where A T alpha alphas are just A alphas. So the weight matrix, the effective weight matrix, so this is like there's a network with like W1 times W2 and then the output here, but this whole thing, the effective weight matrix has a singular value evolution along exactly these right and left eigenvectors coming from the cross correlation matrix, and the eigenvalues these singular value evolution can be written are the values in the diagonal of A here. And sort of this is what's being presented in this figure, that these different modes are being learned at different time. Great. And now, while we're talking of sort of time, let's do a little bit of like time scale analysis, which is like, first, this whole thing requires the learning rate to be really small. This assumption was brought in when we assumed that the change in weights at each sample within an epoch roughly stayed the same. So this was crucial for this assumption to go through. But what does this mean? Like lambda being really small. So it basically means that even the fastest moving singular value doesn't change too much within the time scale of an epoch. And as we saw in the equation for A alpha t, if S1 is the largest singular value coming from the cross correlation, then then from the equation that I wrote in the other board, we can see that tau over S1, order tau over S1 is the time scale to learn the largest mode. And this should not happen too quickly. So we're saying tau over S1 should be much larger than 1. And tau is, as we defined, just 1 over lambda p, and then there's S1 term, which is greater than 1, so imply lambda must be much smaller than 1 over p S1. So this is the kind of time scale, the regime where this whole calculation goes through and is fine. Great. And then there are these other time scale, which is the time scale of learning, right? And they define, because these are asymptotic process, they define learning as if at time 0, this value is 0, the value in the diagonal of the matrix that we're learning was epsilon, and at 8t, it almost reached its fixed point, which is s, so it's s minus epsilon. Then if we go back to the solution of the differential equation that we wrote in terms of time t, and we substitute these values there, what you'll see is you get ln, basically s minus epsilon by epsilon square comes
I have to move over a little bit.
Me, I have to move?
Yeah, just move over a little bit so the orb cam gets the board that you're writing on. That's great. Yep.
Okay.
Thank you.
Is that good?
Yep.
Yeah. So this is a time scale, and 2 comes out, s minus epsilon is roughly s, so there's this tau over s, ln s over epsilon here. So this is the time scale for learning a given mode in deep networks. Now, if you do this TD, let's say, for shallow network, then again, going back to the equation that I wrote in terms of time for the solution of differential equation, what we end up finding is this time scale is tau ln s over epsilon. So the crucial difference is this 1 over s term. So if s is really small, if s is close to 0, the time scale for TS will diverge, and it will take really, really long time to learn this mode in the case of deep network. But if S is really large, then that mode gets learned really quickly in the deep network. But the influence of S is much weaker in the case of the shallow network, as we see here. So this is one interesting difference between I think the main difference that they make the whole paper about is this difference in time scale of learning the modes. And now I just want to go back to this point that I mentioned. I saw this in a talk that Andrew Sachs gave, and I thought it was interesting, which is that now, given that we know everything, we have analytic solution to everything, we can actually start writing the loss function, right? 1 over t sum over 1 to p yi minus y hat I square, and you substitute all the values we have calculated, a alpha t and so on, and what we end up seeing is this is going to be proportional at the end to something like minus sum of alpha over s alpha minus 1 over 2 a alpha d to the power a alpha d, where d is the depth of network. So this is the analytic loss function. It's going to be, there are some other terms before, constant terms and so on, but this is the interesting part. And actually, if you plot it, it's going to look something like this. For d equals to 1 case, this is just a quadratic equation, so it will have some minima like this, just some minima here, where a alpha is s alpha and so on. But when d is larger than 1, then you start getting this weird thing where the loss function looks like this, and as d gets larger, it goes like this. So this part here, where the values of a alphas are 0, which is a saddle point, gets flatter and flatter and flatter as d gets larger. So, and this is why the learning of modes for deeper and deeper network is going to take longer and longer, because at this initial point, saddle is getting more flat as the depth goes up. And I was trying to emphasize this here because I thought this might be interesting for you guys too. It's like flatness of saddle point and whatever. So this is why this is one way to see the difference between shallow network and deep network, where shallow networks don't have this saddle, and for each values it's just going to the minimum of a quadratic term. But for deeper network, the loss function itself kind of has a saddle, and that saddle gets worse and worse for deeper networks. Great, so that's all I have in terms of the technical things. So maybe we can look at the other figure now, and then I will end it.
Sounds good. Yeah, let's all move over to the next set of boards. So this way.
Oh.
All right, I'll put up that slide. That's the one?
Yes. And
okay.
Also the other one,
sorry,
you can put it on the side.
Yeah, you'll have to move over a little bit. The other one, that's right, yeah.
Yes, that part. Great.
Yeah.
So here, let's focus on what's going on in the panel A here. Can I write on top of this? Yes. Okay. Great. Sorry?
It's all right. I'm going to
move just a little bit more so we can see the first figure.
Is that better?
Yep.
Okay. So here they start with creating this artificial data set, which actually historically I think is this is the place where they started the work. McClelland had this work way back where they trained neural networks and did a lot of simulation where they used neural networks basically to take animals into their features. Or maybe I should say living beings, because there's rows and so on.
Right.
Beings to features. So they trained a neural network to show that these features of living beings are learned gradually and one feature at a time by neural network. So this is what we see in the other figure on the left here. This is the figure from the original paper, I think, where they show that first they do this distinction between animal and plant, and then within animal you do this like bird and fish distinction, and within plants then it learns this tree and flower distinction. And here on the right they show that the network when now they can analytically solve this given a certain structure in the data. This is the analytical solution for basically showing that this is indeed the case, and you first start by diverging at the point of like animals and plants, and then learning a finer distinction between fish and birds and plants and trees and so on. So that maybe we can see here. So this is the setup where they have these 4 items, which are like tree, bird, plant, what are these? Fish, bird, tree, plant. Yes. And then on the y-axis, there are the features associated with these things. So a rose has petals and roots, but a salmon doesn't have roots, but it moves and grows, and everything kind of grows also. So this is the structure of the data that they have. They use some generative model to come up with this data such that they can analytically calculate the covariance matrices and so on. But I found the explanation of this generative model pretty hard to decipher exactly what they did to generate this, but either way, this is what they generated. And when you do see, this is the quantity of interest, right, for us, the cross covariance matrix. And when you do SVD on this, of course, this is not a full rank matrix. We're going to see this decomposition into 4 modes. And in fact, these 4 modes correspond to something very interesting. S1 is like the uniform mode. And then starting S2 on the right, these are item modes. So item modes, you can already see in mode number 2, you see a distinction between animals and plants. In mode number 3, then it learns this distinction between fish and bird. And in mode number 4, it learns distinction between tree and plant. And at the same time, there are these like left eigenvectors, which for each mode kind of encode the property. So if the mode number 2 was encoding what's an animal and what's a plant, then you see that there is this distinction between things that fly and swim versus things that have leaves and petals. So this is like the feature per mode. And this is like items per mode kind of distinction. And of course, these are the crucial things that are being learned. And there's actually a really nice video associated with this where you can see these diagonal quantities A1s that we calculated coming to life and just learning the values of S1, S2, S3, and S4. But this is the value that's getting learned throughout the learning process in the deep network. And in this particular case, they can show all these learning behavior, and in fact, they can explain some like interesting cognitive features, which is like because of the nature of deep networks, as we saw, there's this time separation between learning stronger modes and then learning the weaker modes. So at the beginning, little children tend to overgeneralize. And they don't know worms don't have bones because that's too specific, and maybe the time for learning that feature hasn't come yet. And this time scale, the point that they make is this time scale separation between learning modes can explain a lot of like kind of semantic cognitive behavior in like during the growth period of children and so on. Yeah, so I'm just gonna stop there and open everything up if people have questions and points and discussions.
Yeah, thank you very much. Questions for Nisch? I guess I'll ask one. So, as someone who's studying neuroscience yourself, how convincing do you find this? Is this cute, but sort of too much of a toy story? Or do you think this actually is the beginnings of an explanation of some of the basic capabilities of learning systems in the natural world?
I think my point of view is like contrasting it with what other explanations are available for these phenomena. And other available explanations are kind of these Bayesian learning stories. So people like Josh Dunham and other people have like fairly wide Bayesian learning theories of how people, children, and so on come to learn. And in there, they try to explain various like cognitive features such as overgeneralization and so on using Bayesian picture, and compared to that, I think I really prefer this picture where this is very specific to kind of, it's more fine-grained and more mechanistically detailed and still can give rise to some sort of explanation to various cognitive phenomena rather than like a fully Bayesian picture, which is like maybe too many degrees of freedom to replicate like any kind of learning behavior. Like by your choice of constraints and by choice of priors and so on, you can always make a story about like why certain behaviors are observed cognitively. But here I find this to be a much more sort of principled way and like maybe even plausible thing. And in fact, I feel like this like spectral separation of learning not only happens in linear networks, but also if you go into more and look into more complicated networks, this spectral separation of timescale might happen. I actually did that as part of the fellowship for fifth fellowship. I don't have a very concrete evidence, but like kind of evidence hinting towards like separation of timescale in feature learning in like transformer models too. So I feel like while the kind of model that they use to get to this point is very cute and simple, but the point is probably pretty broad and gives us good ideas about what might be happening.